Here's a summary showing some algorithms, their time complexity, and the big O notation associated with that complexity. And here's a summary of the best, worst, and average case for those algorithms. You should be able to recognize graphs associated with the big O notation. If I've got a constant or O1, then I have a horizontal line, and it means that the best, worst, and average case are the same. This means that the time complexity doesn't change as our amount of data grows. An example of this is accessing an array index, or more simply put, retrieving an item from a list using its position number. Our ON complexity is a straight line that's not vertical or horizontal. In this case, the time taken increases in proportion to the data size. Our algorithm that we use in example is linear search. In linear search, if we're lucky, we might find what we're looking for in the very first place we look, which is a best case of O1. Our average and worst case are ON. Of course, if I've got sorted data and I'm searching for something, I could use a binary search strategy. In this case, the graph is O log n. My best case is still O1, where I find what I'm looking for in the first go. But usually, I won't find it in the first go, and I'm looking at a worst or average case of O log n. As the size of our data increases, our line starts to look really similar to that horizontal line. For large data sets, binary search is only slightly worse than our constant O1 search. If we move on to our sorting algorithms, selection sort is an option where the best, worst, and average case are ON squared or quadratic, and that's what the graph looks like. Of course, selection sort is not the best sorting algorithm if we are sorting random data. In that case, we'd be better off using quicksort, which has a complexity of O n log n. And here's the graph. And you'll notice that as our data size increases, our line starts to look a lot like a straight line. And in this case, our n log n complexity is only slightly worse than linear time complexity. But what if we're wanting to have a go at solving the backpack problem? In this case, the complexity is exponential. And here's what the graph looks like. To use brute force, the time complexity would be O 2 to the power of n. This is non-polynomial time, which means using brute force is not practical in the real world. You need to make a special note that the best case for the problem is actually O1. This is the trivial case where either we have no items to put in the backpack or the backpack has no capacity. Our final complexity is factorial, and if we look at our factorial and our exponential graph together, we can see that they are both clearly non-polynomial time. Our factorial is related to our traveling salesman problem as an example, and once again, as we increase our x value, the y value or the number of potential routes increases dramatically. Best case for our traveling salesman problem is if we only have cities, in which case the complexity becomes O1, and this is the trivial case. In your notes, you're wanting to capture both the summary tables and the graphs for bigger rotation, where you note down the best, worst, and average cases. You want to memorize this for the DCAT so that you can confidently answer questions related to big O notation. Remember that anything that is in polynomial time is tractable, and the algorithm is suitable for real-world use. For our exponential and factorials, non-polynomial time complexity is a problem, and that would mean that we need to use a heuristic to find possible solutions in a reasonable amount of time.